Now, unfortunately, I'm going to look this way most of the time because that's actually where my monitor is, but I'm not actively trying to avoid everybody. So welcome, first edition of Mad Pass on the Internet. My video has been spotlighted for everybody. It's really exciting. I'm glad to be here. Who am I? My name is Kevin Feasel. I'm a Microsoft Data Platform MVP out of Durham, North Carolina, where I run a predictive analytics team. Also an author of a book, uh, author of some training courses, blah, blah, blah. I have a blog, Curated SQL. The idea of Curated SQL is I like to try to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. So it's curatedsql.com. And we are going to talk about the apply operator. This is an operator that was introduced in SQL Server 2005. And at its core, you can think of it as semantically similar to a join, but it allows for dependencies between what I am going to refer to as the left side of the data set versus the right side of the data set. And I actually don't know if my camera angles are going to be reversed, in which case I need to do that. But I will try to remember left side, right side. It is difficult on occasion to remember that. But dependencies between the data. Well, this was initially thought of as I'm going to connect to a table valued function. And that was the impetus behind the apply operator existing. There are two variants of apply: cross apply, outer apply. Cross apply is semantically similar to, but not the same as, an inner join. Outer apply, semantically similar to, but not the same as a left outer join. There is no rough equivalency of a right outer join, a full join, or a cross join using apply. What are we doing here? Why are we talking about this? Well, this is a tweet from quite a while ago from Adam Mechanic. It says, if you don't understand the apply operator, there's a lot of growth ability left, because the apply operator, although it is not a one-stop solution for performance tuning, has several places in which it will perform significantly better than most alternatives. It's also, in my experience, a fairly elegant way of solving some classes of problem. And we're going to talk about 4 distinct classes of problem, including one subset of a more general base. If there are questions at any point, please do feel free. Go off mute, stop me, ask questions whenever. And I will try as well, if I can, to follow chat. If I can find that chat window. Here it is. So I will try to follow chat as well if you don't want to ask questions via microphone.
I have a question, and I just have to ask this because it's a word nerd question. So when you say semantically similar, what exactly do you mean by semantically?
So what I mean by this is that the behavior is very similar. The usage, the context in which you would use both is very similar, but internally they can differ in how this apply operation gets translated into the physical operations for SQL Server. Also, the syntax is a little different. So that's why I don't want to say a cross apply is the same as an inner join. It's very similar in usage and behavior, but it's not exactly the same. That's what I mean by it. Let's talk about the year 2005. Actually, let's say 2006 or 2007. SQL Server 2005 is out. Those books have come out, and people have started buying books on what's new in SQL Server 2005 and all the great functionality in there. And in all of those books, there's about that much writing dedicated to the apply operator. The apply operator, these read, is a way that you can join to a table valued function. And then they'll show you maybe an example of joining to a table valued function and then move on. because that's what the apply operator was originally intended for. But it's got a few more uses than that. So let's first, though, focus on that original intent. Here I have an image that shows an error. What I want to do is join sys.dmexec connections to sys.dmexec text. Now, sys.dmexec SQL text is a dynamic management function. It accepts one input. Whoa, I did not mean to zoom, I meant to draw. The most recent SQL handle, and that comes from dmexec connections. So basically, for each current connection, I want to learn what was the most recent SQL statement run for that connection. And I want to learn some info about that. Unfortunately, as you can see in the messages, this does not work. We need a different way to solve this problem. So what do we do? Well, here's the solution those books read. We can use cross-apply. And now we say from dmexec connections, cross-apply sys.dmexec SQL text. We can pass in most recent SQL handle, and from that, select the results that we want. So we build out a result set. And we say, yeah, that seems like it's a good idea. So let's go and try it in a demo. So I think I'm actually going to bump this up to 200%. There we go. I'm on a SQL Server instance. I'm going to select from dmexec connections, and nothing too crazy here. I just want to point out 111 rows, and we've got session IDs. I don't know, the 100 to 200 range. That's really all I want to get to there. So next query is what I gave you in the slide. Cross-apply, dmexec, SQL text. Run this thing. And we get back 24 rows. But we get back some information about sessions. So these are sessions that have queries that have run against them. And some of them are fairly simple queries, like just using a database. Some of them are related to internal operations. But I'm able to get that info. So great. The books were not a lie. So that's good. Difference between cross-apply and outer apply. So this is a cross-apply operation. What if I want to do outer apply? Now I'm going to change this to session number 195 because I have data in here right now. The idea is that with outer apply, I can run this query, and I'm going to get back all of the rows for dmexec connections, regardless of whether I have data in here for text. And we can see 111 rows. So that's good. And we come down here, and by the way, I have session ID 195. If I come down to session ID 195, I no longer have a statement because I set the text to null. So I passed in null instead of the SQL handle. If I change this to cross-apply, my expectation is I'm going to get back quite a bit fewer rows, and probably 23 or thereabout. I also will not get one for 195. We run this, I get 23 rows, and as I zoom in, I do not see 195 anywhere. So great. Difference between cross-apply and outer apply. Cross-apply, like and inner join. It's going to filter out rows that don't have a result on the other side. Outer apply, like a left outer join, will include rows that are missing elements on the other side. And that was the first demo. Any questions so far about this? If this was the year 2007, we'd be like, sweet, presentation over. Let's go home. But this is not the year 2007. And therefore, I get to continue on. See, if that was the only thing the apply operator could do, I definitely would not be giving this talk. I don't like table valued functions to begin with. I accept them when they are dynamic management functions because that is the way things operate. I don't like creating them or working with them, and generally do my best to eliminate them whenever I can. So if that was the only use of the apply operator, it probably would not be something of which I am fond. Nonetheless, I will say that when it comes to executing table valued functions as though they were tables, apply does a really good job. And outer apply will show you rows that cross apply may filter out. There are some mechanics behind that, but that was probably the least interesting part of this. Now we start getting into what I think is the really interesting part of the apply operator, and that is to assist developers in understanding code. So we're going to start by pre-aggregating some data. I've got water bottles for sale, and I want to figure out how many times somebody has purchased a particular type of water bottle. I also want to learn a little bit about the product category and subcategory. So, all right, we're using AdventureWorks, and if you know the AdventureWorks database, you could probably write this query from memory. Let's start up at the top here. The query is a little lengthy, but basically from product category, joined a subcategory, joined a product, joined a sales order detail, we're going to get water bottle 30 ounce. So products that are named water bottle 30 ounce. I would like to get some non-aggregated details like the category, subcategory name. I also want to get an aggregation, the count, the number of purchases. Well, because I have an aggregation function and I have non-aggregated columns, I need a group by clause that includes all my non-aggregated columns. And that's going to give me back my data. But let me show you something else. This starts off very similarly. Category, joined a subcategory, joined a product. But then we throw in a cross apply. So inside my cross apply, I have another unique SQL statement. The count from sales order detail where product ID, so in other words, the product ID from here is equal to the internal sales order detail, SAD, dot product ID. So this independent query executes once per record and will give us the count where those product IDs tie together. What's interesting about it is the aggregation goes away from my outside query because I get back a single row for detail. And I just call that detail count. So let's go check that out in a demo, see how it works, and see why it's exciting to me. I'm going to close this. Next, pre-aggregate data. All right, I will not set statistics.io or time on. Instead, we're going to use SentryOne Plan Explorer. But basically, these are the two queries that I came up with before. So this is the basic query, the normal query. And by the way, let me just run these two just to show you. They do give you back the same number of rows. So they work the same. The behavior is the same. But I have this cross apply operation that makes things a little special. So let me see where I put SentryOne Plan Explorer. It's right here. Let's paste, get the actual plan. We're going to connect to AdventureWorks 2012. Let that run. And I'm going to zoom in once it starts getting exciting. I think it's exciting now. Our first query, our basic query, took about 14 milliseconds to compile, 100 milliseconds to run, 771 reads. Our apply operator query took a quarter of the time to run, a quarter of the CPU time, same number of reads. You might ask why. They're doing the same thing. So let's go look at the execution plans. This is what the plan looks like for my basic query. I need to perform an index seek on sales order detail enlarged. It turns out that there are 187,520 separate purchases of this water bottle. Well, I'm going to need to aggregate that data and connect it. So this is the version. This is the apply version. Yep. Sorry. Jeez, I'm all out of sorts here. All right. Here is the version that is the normal version. I already gave away the secret for the apply operator version. Here's the normal version. One product, and I go look up some info about it. I get info on the subcategory. I get info on the category. So far, it's just one row joining to one row. Then I need to nested loop join to the number of times it's been sold. Well, there are 187,520 times this has been sold. So I have a nested loop join where I have one row on the outside. So one rotation on the outside, 187,000 rotations on the inside. And then we aggregate the results to get back our count of 187,520. By contrast, here's the apply operator version, which I've already spoiled, where this first part is the same. But here's where things get a little different. We have a nested loop join that comes down to our index seek. We still have to pull the same number of rows. We still have to get that out of the buffers. It's going to take the same number of reads, but we can immediately aggregate down to one row. And now our nested loop join is one row and one row inside. That's going to reduce CPU burden. And as a result, the query ends up being faster, despite the fact that they give you back the same results. So in that sort of scenario, apply can work better. Here are lessons learned. Number one, we can use apply to return data from these sorts of functions. And I've called them ad hoc functions. I've called them derived functions. I've heard people call them both of those. I'll probably call them both just to keep things interesting. But basically, that is a function that is not specifically defined as a user-defined function. It is ad hoc, runs through in the context of a single query, and can be connected together as part of the execution plan. That's part of how it performs better than a separate user-defined function. There are other ways to pre-aggregate this data. I won't tell you that the apply operator is the only method. You can use other methods. Subqueries work for this as well. And in this case, apply worked better than the base query, than the simple query, because we were able to aggregate early to reduce that nested loop join down to one row on the inside, and therefore reduce the amount of CPU cost of performing that join. By doing that, we got rid of 3/4 of the CPU cost. Not every query is going to have that drastic of a change. Many queries probably won't be that much of a change. But in this type of a scenario where I go from a lot of rows down to a very small number, the quicker I can get down to a small number of rows, the better off I am. And that's what apply helps us do. Any questions so far? I've lost chat, so if you have questions in chat, I'm not able to see them right now. But I'll go on and talk about specific child records. So let's say I'm going to look at some orders for people. And specifically, I want to learn about the customer's latest order, the PO number associated with each order, and the total amount due on each order. And I can do this. Business side comes to me and says, Kevin, we need this information. I go to my thinking corner and I come back and say, well, there's a few different ways I can do this. Nested subquery, common table expression with a window function, derived function with apply. Business people look at me with kind of wide eyes, like, what is this man talking about? Do we need to call any officials, any authorities? And I just continue on explaining to them that there are other options as well. I mean, I could use a cursor or a while loop, but that sort of rebar operation isn't necessary for this work. I can easily solve it with set-based solutions. By this time, their eyes are usually kind of falling back in their head, the drool's coming out. I continue on by saying, I mean, I could also create temporary tables and stored some of the data portions of the query in these temp tables and join the temp tables together to get my results. But that adds a layer of complexity. And if I can get good performance without that, I'd rather take the good performance than maybe if I could eke out a little more, unless I really need it. And I don't need that performance, do I? And by this time, the business people are willing to agree with me just to get me to go away. So they say, no, do whatever, just please let me leave. And that's how most of my meetings go. So let's take a look at this in a demo. Latest and or greatest child record. To give you a feeling for what we're looking for, count of customers joined to persons in this database, 19,119. So that's the number that I'm looking to get back. First method, correlated subquery. In case you've never heard of what this is, here's the idea. We have customer joined a person. You're going to see that quite a bit in the next couple of demos. So customer joined a person, just going to happen. Then we have a subquery. So we have left outer join, and inside this subquery from sales order header, I would like to get the customer ID and the latest sales order ID. Now, I'm taking advantage of the fact that sales order ID increases monotonically with respect to order date, by which I mean that they both go in the same direction. You don't have later order dates with lower sales order IDs. This turns out to make nested subqueries relatively more efficient. If I didn't have that trait, it would actually be a lot harder to solve this problem using a nested subquery. Nonetheless, I need to get that order ID. So I get the latest order ID per customer, group by customer, and this forms my nested subquery. Only problem is I need to get more than just the sales order ID. I need to get the purchase order, the order date, the total due. In order to do that, I need to join back to sales order header again. Next solution, common table expression using a window function. And really it's the window function doing most of the heavy lifting here. So from sales order header, I would like to get my sales information, which includes those columns. Then I want to get a unique ascending row number for each customer based on their sales order in descending order. And I'm going to get that and call it row num. So what we see is for a given customer, we have a unique ascending row number per customer based on the order date. actually technically based on the sales order ID. So we get those results. And I'm going to take sales customer joined a person, left outer join this common table expression that I have called orders, where row number is equal to 1. That is, I only want the first order. That is by sales order ID descending. And if I jump in and look at this data, we see for customer 11,000 that their first order was in 2005. Their second order was in 2007 on July, and their last order was 2007 in November. We want that last order, which just happens to always be numbered 1. So we're looking good. Third option, derived function using apply. From sales customer joined a person, we outer apply and say, give me from sales order header the top 1 set of details where customer ID matches up, ordered by sales order ID descending. Each one of these should give me back 19,119 results, which adds up to 53,357. If I look at these individually, they are all 19,119. And by the way, if I look at the details, they're exactly the same. All of the results are the same for these 3 queries. So let's go pull it into Century 1 Plan Explorer and see what that brings us. So at this point, I'm going to hit OK. It's going to run those 3 queries. And what we're going to find, obviously, because I'm talking about it, is that the apply operator is the best answer for this problem. So once it's done, it's just going to tell us that, yeah, apply, that's the best case. We just can't do anything other than apply. And query execution has started. The problem is that there is a stupid function in AdventureWorks around this where it takes forever in Century 1 Plan Explorer. So it kind of ruins the joke that I'm going for. So I'm going to run as well a actual execution plan in SQL Server. And one of these days when Century 1's done running that function 50 some thousand times and calculating details on it, we'll see over there. But here's our first query. Nested subquery, relative cost 30%. Here's our second query. Common table expression with window function, relative cost 15%. Those of you who are good at math have already realized that the apply operator, you know, the thing that you brought me here to talk about, is doing the worst of the 3. So I think there is some explaining to do, and that explaining comes in the form of understanding the query plans, which I would hope to do here, but that's all right. I'll just do it in Management Studio. So let's drag this up a little bit and employ intense zoom it skills. So I'm going to drag you down. There we go. What do we have? Well, this part, sales order header joined a sales order header. We're going to think about that. This part down here, customer joined a person, this will be the same for all of our queries. So I don't really have to think about it. The behavior is the same across all 3. So instead, we focus on the top box. Sales order header, we have a scan of the index. So 31,465 records get pulled in. We aggregate down to 19,119. So in other words, aggregating by the customer ID. We have 19,119 customers. Then we need to get the remaining details for sales order header. So I need to connect those together and join them. We'll do a hash match to join them together. We have these 2 hash match outputs. So this one has 19,119. This one also has the same. And we're going to do one final hash match to bring them all together. Let's look at the second query. This one, a little simpler to understand. As mentioned, ignore the bottom because that's just customer joined a person. So along the top, index scan. So we still have an index scan, pulling in all of the rows. Then we have a compute scalar to do some calculation work, segment, sequence, project, and then filter. So these...
Kevin, this is a CTE, right?
Correct. This is the
Okay.
common table expression using
Okay.
a window function.
Okay.
And this part right here that I've got highlighted in the box, that's the window function. When you see segment, sequence, project, usually that's a window function. And then we have a filter. So in other words, we have to calculate the row number for all rows. And then we can filter down to just the 19,000 that we need. And then we have a hash match over here that looks like it's spilled over just a little bit. Finally, the apply operator version. See why this thing is so bad. So bad because I got to keep dragging. Oh, well, that's just rude. All right, we're gonna do it this way. Because this was customer in person anyhow, so forget those.
Is Century 1 done yet?
Let's find out. It is done, and it's given us all, here we go. Ignore all the function stuff. There we are. So this is nested subquery. And I'd like to hide that. Nested subquery. We can see the red boxes there. This is our apply operator. And basically what we have is for each of our 19,000 customers, we're going to do a nested loop join and go down and give me the top record from sales order header. So I'm going to do this 19,119 times. The main problem with this, we can see up here. All three of them have roughly the same CPU cost, but the apply operator has 2 orders of magnitude more reads because it's doing 19,000 seeks of the data rather than 1 scan of the data. So here's my conjecture. This performs really poorly because I need to get approximately 2/3 of the total amount of data in order to return my query results. If this number, this 19,119, was a lot smaller of a percentage of this number, then apply becomes more interesting to us. That's my conjecture. So let's conject away. And I'm going to run this query. And while I'm running it, we will look at it. So this looks very similar to what we had before, except look at the sales order header enlarged table. Sales order header enlarged is a much larger version. Sales order header has 31,000. Enlarged should have about 1.25 million. Yep, here it is, 1.25 million. So we're talking a couple orders of magnitude bigger. And that is important to us. This is going to take a hot minute. But the only difference, sales order header enlarged. We come down here, sales order header enlarged. We come down here, enlarged. Otherwise, the queries are the same. So while the Century 1 Plan Explorer version is running, let's take a look at this. Make sure that we get back the same results. They all come back. In my execution plan, what's interesting is relative percentages. This is the nested subquery. it is now responsible for about 3/5 of the total expected cost. That may be different from the real cost. We'll see what the real cost looks like soon. Common table expression, 26%. Doing the math, that doesn't leave very much for the apply operator. And looks like this is still burning away. So let's talk about what happens and why. For query the first, we still have customer joined a person. We can still ignore that because it's still the same as before. It's still 19,119 results. But for each one of these 19,119 customers, we are performing a nested loop join. The query plan has changed for the nested subquery. Now it's a nested loop join, and that is seeking sales order header and large to get back the top row for each one. Very similar to what the apply operator was doing first. Then we hash match and say, I need to get back the details on each one of those. And the optimizer says, I got nothing, just scan that table. So it was doing an interesting job, and then it just gave up and said, scan it. Scan it a second time. The common table expression with a window function starts with an index scan of 1.25 million rows, performs the same work as before to get down to 19,000 rows. And otherwise, basically it looks the same. The apply operator version. Let's take a look at it in here. The apply operator version looks exactly the same because it is exactly the same plan. The plan is still for each one of these, go get the top entry in this table. So it's still executing once per customer. But here's the difference. CPU time, cut roughly in half. Duration, cut 20-30% off. Number of reads is still the highest. Although the nested subquery ends up being pretty close. Number of reads for the common table expression is fairly low because it's scanning everything, but that has the highest cost, if by a small margin. It takes compute to scan a large amount. And if that table wasn't 1 million, if it was 10 million, 100 million, a billion, that increases the compute cost of performing a scan even further. It increases the memory costs of performing those scans versus this apply operator, which I could have a billion rows in that sales order detail and large table, and it says, whatever, I'm just pulling back one per customer. So this can scale effectively linearly. I can add orders of magnitude to the number of rows in my child table and not care as long as the number of rows in my parent table remains the same. The apply operator cost grows with respect to the number of rows in the parent table and the percentage of rows in the child table that we care about. Summarizing this up, the nested subquery version generally is going to be worse than the common table expression with a window function. There's nothing about the common table expression or nested subquery itself that's inherently bad. It's really window function versus not window function. The window function version doesn't scale well. It's going to work pretty well for a million rows. We saw that it worked okay for a million rows. It was worse than the apply operator, but still 700 milliseconds versus 300 milliseconds. Or 2.1 seconds to run versus 2.5 for the window function. But it's going to scale, it's going to perform worse and worse relative to the apply operator as that denominator grows larger, as that child table size grows larger. The apply operator is relatively inefficient for small loads because we're doing seeks, but it scales extremely well. If you're dealing with a small data set, by small data set, I don't know, a few 100,000 rows, maybe 1 million rows, pick whichever one you like, as they're all going to perform about the same. When you start talking about 10 million rows, 100 million rows, even in the several million range, apply operator starts to pull away from the pack. Questions about that? All right, in that case, let's get the top in rows for each thing. This is actually just a general form of the get the specific child record, get the latest row. Basically get the latest in rows. So I want to see some descriptive statistics on the 5 latest orders for each customer. Again, I go to the table and I say, well, I can nested subquery, common table expression with window function, derive function with apply. But the nested subquery becomes a little tricky to write because we need to get more than just one row, so I can't use max anymore. So we also know from the prior example that it's not going to hold pace with the window function, and at scale, it's not going to hold up with apply. So let's not even concern ourselves with that one. And instead, we'll jump right into the demo. Demo 4. I'm debating whether I even want to show you the original version. I'll show you this version just to give you a feeling. This is the small data set, 19,119 clients. And here's our common table expression with a window function. From sales order header, give me the customer ID and the total amount due, and also give me a unique ascending row number based on the customer, order by their order's date or order ID, descending, and call that thing row num. Then we're going to call the common table expression orders once again for orders. So we'll join customer and person to this orders common table expression, getting back the 5 latest orders, assuming that there are 5. If there are only 3, we get the 3. We have some details about the customer. We have some aggregation functions, some descriptive statistics. Whoops, number of orders, min, max, average, and sum of total due. Because I have all of these aggregation functions and I have these non-aggregated columns, I do need a group by clause, which includes my non-aggregated columns. Here's the apply operator version. Customer joined a person, and then we apply from sales order header, where customer ID in the sales order header matches my customer ID up here. Give me the top 5 customers and total due, and call this derived function O. So now we have calculations, O.total due, and we have non-calculated columns. So I need that group by, and I can run these, and we'll see how SentryOne Plan Explorer likes this one. Okay, this isn't as bad, he says before it becomes this bad. So give that a moment. Check this out. The data sets are the same. Both of them have 19,119 rows. Both of them will have the same details, the same information. I can execute an actual query plan, and the cost estimation says that about 1/3 of the cost goes to the window function. About 2/3 of the cost goes to the apply operator version. Once Century One Plan Explorer is happy with our going through this function over and over, we'll be able to figure out what it says for times. But most likely, I'll just lay it out that the apply operator is not going to perform very well compared to the window function for this small data set. And why is that? Because we're getting 31,000 rows out of this table. Our filter keeps 29,786 of those rows. So we're actually pulling about 95% of the data from this table. And for the apply operator, that means that we are seeking and pulling 5 rows at a time and effectively getting out 95% of the data with little pokes. So performance will not be good for the apply operator version. And I will turn statistics, time, and IO on and show you it this way. So 753 milliseconds elapsed time for the window function version, 219 milliseconds of CPU. Not much in the way of reads. Here, 40,000 logical reads took 297 milliseconds of CPU, so more CPU, took about twice as long for the query to run. So yeah, as we expected, apply operator didn't work on the small data set. When we talk about the larger data set, the 1.25 million rows, let's run these. And now the tables have kind of turned. So the elapsed time for the window function, 900 milliseconds. For the apply operator, 700 milliseconds. CPU's gone down. So we've gained in CPU. Our logical reads hasn't really changed much. Over here, we've got an order of magnitude higher in terms of logical reads, but it's still an order of magnitude lower than what the apply operator does. But this gets you to the point that if I look at, these two, that was 40,000 reads. This is 60,000 reads, despite the fact that I have 2 orders of magnitude more data in this table. I'm actually not reading that much more of it. And that leads to a benefit where that table gets larger and larger. The number of pages read doesn't grow commensurately. It'll grow a little bit as our indexes get larger, as our B trees get wider and deeper, but it doesn't really change that much. Not until you get past like 2 or 3 billion rows, then you get another level on the page for the index. But at that point, now it's like 5 pages to seek to a row as opposed to 4 pages. So it adds up, it adds more, but it's not a huge difference. And here was what our run looked like in Century One Plan Explorer, where we have the apply operator being just a little bit worse. So there is some variance in terms of performance, but basically the apply operator not as good for the small data set, but does work better for the large data set. And as that data set gets larger and larger, apply works better and better relative to the alternatives. So similar to the specific scenario, apply starts off kind of slow, starts off kind of weak, but really picks up as you add more and more data to that child table. So let me summarize and talk about when is the apply operator more efficient? And the answer is not always. I picked out these cases because this is instances of a form when the apply operator can perform better. Apply will run one time for each element in that parent or that left-hand side. And because each iteration is unique, apply will almost always generate a nested loop join. There are cases when it does not generate a nested loop join. Most of the time, if your apply operator does not generate a nested loop join, you don't have a good index and query performance will be awful. There are rare occasions when it doesn't do a nested loop join, but it's still really fast. We won't talk about that right now. That's rare enough that you're not going to find it too often. But for this sort of point lookup, I want to see a nested loop join. That's how I want to see the apply operation implemented. And most of the time it is. So the ideal scenario for apply, not that many parent records, a huge number of child records, and relatively few interesting child records. So I want the top 5 orders, but I want people to average 1,000 orders, because then I get a very small percentage of the total number of orders. And in other words, here I am seeking 19,119, and I want to reduce the number of parent records, reduce the number of customers if I can. I want to increase the number of child rows if I need to. I at least can handle that scale better. And I want to have a nested loop join where that parent connects to the child. So this is actually a really good execution plan for using apply. Like, this is the type of plan I want to get toward, because I'm getting a very small percentage of sales order header enlarged. So how small is very small? Well, we'll talk about that in a moment, because apparently I'm a slide too early. This one also worked very well for us because we had one parent row and one child row effectively. If I had 10,000 products, I would be performing 10,000 separate aggregations. And performance probably would not be that great. We might look at other methods, but because I'm focusing on one product, I've minimized the number of parent rows. Then minimizing the number of child rows that are interesting helps. I can't do that much here, but I can aggregate early to get down to one row in the nested loop. So here's the next slide that I was trying to jump toward. Relatively few interesting rows out of a huge number of total rows. It's kind of a verbose way of saying, I want an index seek instead of an index scan. And you ask somebody, okay, at what point do you want to seek as opposed to scan an index? And this is a rule of thumb. There are obviously scenarios where it can be different, but rule of thumb wise, anything above about 20% of the data, you want to scan. So if you're pulling back, let's say you have 1 million rows in a table and you're pulling back 200,000 or more of those rows, you generally want to scan. And if the index, if the execution plan says index seek, but it performed a scan, that's the same thing. If you want to pull back less than 0.5% of rows, you definitely want to seek. Between that spot, it depends. Sometimes a scan will be faster, sometimes the repeated seeks will be faster. Well, for our first scenario, we got 19,000 out of 1.2 million. So that is about, what, 0.1%? That's putting us squarely into the seek zone. That's why performance was unabashedly better for the apply operator in that first case, especially when it came to CPU. When it came to reads, it wasn't all that great, but it was definitely better in CPU. For the second case, where we got the top 5 records, my recollection is that's somewhere around 8% or so of the total amount of data in that table. Puts us squarely in the it depends zone. And that's kind of what we saw in the example, where At 1.2 million, apply ended up being a little faster than the window function, but not a huge amount faster. Not so clearly faster that it became obvious that you need to use it. But it did become a little faster. So as we move towards smaller and smaller percentages of the data that we find interesting for a query, apply becomes better and better of a choice for us versus other operations like a window function that requires a scan. Consequently, apply will perform poorly if you need to scan for each parent row. So that's where I mentioned if you have a no index or a bad index and you have to scan 19,000 times, that's way worse than scanning once, obviously. So we want to watch out for that. We want to force into seeks, into very small point lookups, as opposed to broader based scans. If we have an enormous number of parent rows, or we need to get almost the entirety of the child rows, at that point, it's usually better just to take the hit and perform a scan. Questions about any of that? Okay, well, this ends the performance part of tonight's talk. Talk about what I think is actually the most fun, simplifying calculations. SQL Server calculations tend to be kind of repetitive, and apply can help us remove repetition in our queries because we can feed the results of one derived function into the next derived function. I've shown you how you can take a table and join that within the derived function to link them together. But we can do the same thing with derived functions. So here's an example. Sales order detail, and I need to perform some calculations. So I have list price. List price is the order quantity times the unit price. I want to get the discount amount. And in order to do that, I get the list price, I multiply by the unit discount amount, or unit price discount, and that gives me the amount. I want to get the calculated line total, which means I need to get the list price. I want to get other things. We can see list price shows up over and over. And I have to reference it by the calculation every time because I can't reference list price in the same select clause that I defined it. Here's another example, calculated line total. It shows up here. It also shows up in a couple other spots. So we have these calculations that are just copy, paste, copy, paste. And sometimes you make mistakes during copy, paste. Sometimes the formula changes, but you forget to update all of the versions, and you can end up with bad results. So here's what it looks like with the apply operation. First, sales order detail, I cross apply, and I can select quantity times unit price. One thing I want to point out, there's no from clause here. So all I have is a select operation. What this means is I'm not hitting another table. This cross apply will be implemented as a compute scalar. It has effectively no cost. Very, very close to no cost. Then I call this thing LP. And I can reference LP in my select clause. I can reference LP in later cross-apply operations and get calculated line item. I can reference calculated line item down here in other places as well. So we get to see how we can reuse the results of these formulas without having to copy and paste the formulas themselves. If I need to change the way I calculate list price, I'm changing it in one spot, which for a developer, that's a thing that we want. I can also see calculated difference being used over here. So let's go check this out in a demo. Here's demo 5. All right. This demo is like Law and Order, based on a factual case, but names have been changed to protect the innocent. So this actually was something that I had to deal with at my job at one point. We have a fact table and we have some data. So for a date, we have a set of sources, and those sources give us click data and cost data for digital marketing work. But I have two separate sources that give us cost and click information. I have one source that gives us order information. And there's a question, which source do I use? Click source 1 or click source 2? Cost source 1 or 2? So I've got a Boolean flag that tells us whether or not to use source 1 or source 2. And here's some data. So sometimes I have data for source 1, but not for source 2. Sometimes I have it for source 2, but not 1. Sometimes I have it for both. But it tells me which source I should use. Here is a query. I don't want you to try to discern what's going on here because it's going to be a little tough, especially with me scrolling like this. I just want you to kind of unfocus your eyes a little bit and look at all of these, all this pink, all this blue, the relative paucity of the color black on here, where pink is functions, blue is special operations. This entire query is just swarming with that. Now, focus your eyes in a little bit again. And I have this is null order count. I have is null order count, is null order count. I see order count a bunch of different times. I see these calculations repeated over and over. If I run the query, I do in fact get back results. It is a functional working query, but I think I can do better than this. Let's do it. So here, start with fact, cross apply. And the first thing I want to do is all of these is nulls. And you might ask yourself, why is this guy doing is null when performing a summation? And the answer is kind of dumb, but funny. So a company I work for, at one point, like I said, I had to deal with this query. I asked about the is null because if you run the query and it doesn't have is null, it still gives you the same results. But let's, I don't know, let's remove one of these is nulls. I'm afraid of removing too many of them. Okay, so we remove the one, and I think that should be enough to, oh, sorry. There we go. To give us this little message, warning, null values eliminated. The data access layer that existed about a decade ago for this company was written in, I think, C++, and would take back anything that came back from SQL Server as result sets. It actually took this warning message as a second result set, said, wait, I only expected one result set, and would throw an error. Therefore, at that time, the company did not allow for any sort of warning message on aggregation because that would actually cause the code to break. Kind of silly, but it was a real thing. That has been fixed since then. But anyhow, first thing I'm doing here is all of my is nulls. I just want to do them once, get it over with. Call that no null. So I have fact and I have no null, and I can take and say when I need to use source 1. So dbo.fact, use source 1, then give me no null click source 1. Otherwise, give me no null click source 2 and just call that thing clicks. I only need to do the calculation once. So come up here and we find out that these calculations actually aren't as difficult as they looked once we do a little bit of calculation cleanup. Order count, order revenue, product cost, those are just summations. This conversion rate, I can walk you through it and say, oh, well, it looks like these are just guard clauses And really the formula is essentially number of orders divided by number of clicks. That's the conversion rate. Well, this formula makes a lot of sense. Whereas if you show somebody this formula right here, it is the same thing mathematically, but for a human developer to read this is a lot more painful. So giving us the simplified version of the calculation lets us run this, get results, and by the way, the results will be exactly the same. And the execution plans will be very close to the same. The only difference between these two plans is that there's a loop join on a constant scan. Doesn't really add anything in terms of cost, but does add that little tiny bit of extra weirdness to the query plan. And just to show you, all of those cross applies come at basically zero cost. Here are, well, can't do that. Here are my two queries. CPU of both is essentially negligible. Number of reads is negligible. They're essentially the same plan, and they don't take much at all. Here's another example. And from this table, so I've got a list of numbers that are comma separated. What I want to do is figure out a quick calculation, easy calculation. I want to know where the third number is less than 50 and order by the fourth number. And by the way, third number less than 50, order by fourth number. Well, if I don't have any extra numbers, I actually want those to be 0. So here's how we do it. First step, select star from this table. Just to show you, we've got a list of numbers in that table. It's just a string. We need to break it up and do some work with it. Here is a perfectly functional query that gets us back cases where the third number is less than 50, ordered by the fourth number. This is not a query I want to deal with. It's not a query that I want to troubleshoot. There are far too many char indexes for my liking. So let's try to do it a different way. And here is what I would consider to be a much clearer version that still gives us the same results. Num4 is less than 50, order by num3. Much easier to follow as a person. But let's take this step by step. First, select star from T and cross apply, select work string. So what are we doing? We're adding 4 commas to this because I mentioned that I need to know the third number and the fourth number in this list. I really don't care about anything beyond 4. So I'm going to add 4 commas just in case we don't have enough commas. So for this one, this first element, obviously it doesn't matter. But for the second one, it does matter. I only had 1 comma and I needed more. Okay, then let's get the locations of the first 4 commas in each row. And how am I going to do that? Well, give me the character index of the first comma in work string. And I'm going to call that P1. Then give me the first comma in work string after P1. And I'll call that thing P2. And I'm going to call this function of P2. Then give me the first comma in work string after P2. First comma in work string after P3. So I iteratively look through, at least as a developer, my developer lizard brain says I'm iteratively looking through and getting the locations of the first 4 commas in this string. Well, what I can do with that is realize that the number is the stuff that is before the next comma and after the current comma. So I've got all of my commas, and then I can say number 3 is equal to the substring of workstring, everything after the second comma, up to but not including the third comma. Number 4 is everything after the third comma, up to but not including the fourth comma. I can run the query. I get back my results. And again, if I run this as, let's just pull it into Century 1 Plan Explorer. Remove the select star from T. Run this, and we're going to see that it will actually be the same query plan. This one is not very exciting at all because it is literally the same query plan. All of that extra apply work, every last bit of it goes into this compute scalar. But the thing is, the compute scalar still has to happen because we're still performing calculations. So we're still calculating number 3 and number 4 in our nasty version of the query as we are in the apply version of the query. So we still have the same work being done. It's just this one, I can hand to a developer and say, well, golly, it sounds like the business side really meant to say number 2 is less than 50, less than 30. Really weird. They told me number 3 is less than 50. So go fix the query. And you can talk about, oh, how's the wife and kids? They're doing great. How's everything going? It's almost baseball season, isn't it? And then, yeah, okay, great. Well, looks like we had nothing under 30, so get out of my office. Sorry, the business meant 90, not 30. There we go. And in just a couple of moments, while I'm talking, while I'm jibber jabbering, I can give you a new version of the query, even adding a new component that solves the problem. Cannot jibber jabber and give you a version of this that solves that problem. This is going to be a little more painful, having to deconstruct the elements. I'm not even going to try it here because I'll get it wrong. So that's where cross apply can really make life easier for a person. You have complicated queries. This one is a little extreme, but like I said, this actually is real life. This is something that I had to deal with. This is actually a simplified version of what I've had to deal with. So there are plenty of places where the apply operator can help you remove repetition from calculations. Wrapping things up. Apply excels at a few different activities: pre-aggregation of data, subsets of child records for each parent record, simplifying calculations, especially if you don't want performance to suffer as a result, or splitting strings. Now, mind you, this is not a cure-all operator. This is not going to solve all of your issues around bad performance. But what it will do is, in certain circumstances, will help you considerably with performance, especially in cases, like we mentioned, around lots of parent rows of which you want a relatively small number, huge number of child rows of which you want a relatively small percent. If you'd like to learn more, grab the slides, grab the code, get information about additional resources. Go to csmore.info/on/apply. And I'm putting these in chat, by the way. If you have questions, please feel free to hit me up via email or by Twitter, where I'm on maybe once a week. By the way, I have a much more, or somewhat more detailed version of this talk that is available on Teachable. It's $40, but if you use the code feedback, it's 20% off, or 50% off. So it's $20. Basically, $20 gets you more than this content. I go into more cases around the apply operator. I dive into it a bit deeper, and there's a lot more instruction on that. So if you're interested, go check that out. Feedback, the code gives you 50% off. And with that, anybody have any questions? I think I filibustered them successfully.
Yeah, this is pretty awesome.
Yeah, I couldn't believe how much more readable the code was. That's impressive.
Yeah, and you know, this is I would say probably like the 90th percentile solution, by which I mean 90% of the code that I write and work with is much less complicated than this. But as that code gets more complicated, especially if you're repeating these calculations just over and over and over, which often you'll do in reporting, you can absolutely simplify what things look like at the end.
Cool. Anyone else? Any other questions?
Is it
All right, awesome.
that operator on the development engine by default, or does it you have to go get it?
No, the apply operator is part of SQL Server. It's been there since 2005.
Good.
And it really hasn't changed since 2005. So no matter what version of SQL Server you're on, behavior will be the same.
Good.
So Brigitte, can you refresh my memory? Are you going to send out an email on where this is recorded?
Yes. Let me